Yeah, all right. So I guess welcome everyone. And today we're very pleased to have Makoto Yamada from Kyoto University and the Recon Artificial Intelligence Project, who's going to talk about selective inference with kernels. So yeah, please start your talk when you're ready.
Yeah, thank you for the introduction, Oscar. So I'm very happy to have a seminar today at the UCL. So today I want to talk about the selective inference with kernels. And so this talk is about 45 minutes in total. But if you have any questions, please feel free to interrupt me, or you can just put some question into the chat box. Okay, so today the seminar is about the selective inference. So I'm not sure many people are familiar with selective inference, but the selective inference is basically one of the hypothesis testing. In classical hypothesis testing approach, we have a hypothesis first, like ML model, and then after that, we collect the data. Then we test hypothesis. So this is a classical approach. But for the selective inference, is a bit different. We first have a set of data set, and then we decide hypothesis, and then test hypothesis. So this is the difference between the classical approach and selective inference. So this case, for example, like we can we have a data and then we select the features from data, or we select some data set among the entire data set, or we can build the models and from the data and then test. So in this case, there's a problem because we build a hypothesis based on the data set. So therefore, it is a bit difficult to control the false discovery rate because we build a model to get important features, because the important feature is to select based on the maximum HSIC or something. So therefore, if we do the testing based on the same data set, we tend to have a false discovery a lot. So before going further, I want to explain about what is how to select features, how to select the data set, how to select the model first. So I think many of you know about feature selection, or this is also known as a variable selection. So this is to select important features from data. For example, this is an illustration for the supervised feature selection problem. So this is the images of the gene expression data. Y-axis is the samples or patient, and x-axis the features. And for each samples or each patient, we have label. So this label could be like this patient is a cancer or this is non-cancer, for example. Then we want to know which genes is important. Then if we can find important genes, then we can do the maybe drug discovery in the end. So this is just a feature selection problem. So feature selection is basically we select the columns of this data matrix by using this label information. This is a supervised version of it. So this is one way to select the set. And so this is the format definition of a proper formulation of feature selection. So we have an input and output pair. Input is a d-dimensional vector, and y is this is the outcome. So we have a n sample of a paired its genes and its outcome, and this is from the pxy. So basically, we select a small number of features of x. This is a d-dimensional vector that represents its output y. So this is just a feature selection problem. So another types of selection is a data set selection. For example, selecting important data sets. So this also can be done. For example, we have some reference data set and we have some other data sets. And we want to know which data set is similar to the reference data set or which data set is better than which. So this is the kinds of data set selection. So this is one of the application. So for example, in generative adversarial nets case, the GANs evaluation, we have a reference data set. So this is the true images. And then for the GANs case, we generated a lots of images. For this is one GANs, we have generated images from the one GAN. So this is the another GANs generated images. And we want to know which GANs is the best. So in such case, this problem can be formulated as this one. So basically, we want to compare the data set with the reference data. Also, we can do the model selection. So this is simply replace the data sets to its models. For example, again, we have some reference data set. So this is the N samples. And we have L number of models, like Q1, Q2, QL, they are models. For example, this is a truth data set. This is actually corresponds to a reference data set. We build the model for like MOG and MAID and MAF. So in this case, we have 5 models, and we want to select which model is the best. So this is also model selection. Okay, so then this is kind of summary of this seminar. So actually, I introduced the selective inference with kernels. So basically, as I said before, I talk about hypothesis testing, but this is a not classical approach. This is based on the selective inference paradigm. So we have, I introduced 3 types of selective tests. One is called the selective independence test. This can be used for the feature selection. Also, selective 2-sample test. This can be used for dataset selection. Also, this can be used for the binary classification problems. Also, the selective goodness of fit test. This is for model selection. For the selective independence test case, basically, so I think many of you know about HSIC at UCL, I think. But basically, we use the HSIC for the independence measure. So basically, if we do not have these conditions, so this is a typical independence test setup. But only the difference is that we first select some features. Oh, sorry. First features, then with this condition, we do the hypothesis testing. So this is the selective independence test. Also, we consider about selective 2-sample test. This is, we use the simply MMD, because MMD can be used for the 2-sample testing. And also a goodness fit test, we use the Kernel Stein Discrepancy. So this is a kind of summary, and I'll talk about how to do this in details.
Hi, can I ask a question?
Yes, yes.
So basically, you pick a feature M, and then you decide which one you're going to test just that feature with a label. Is that what you're doing?
Yes, yes.
Okay,
so that's for the selective independence test. So I'll talk about more details in later slides, but basically this set S could be a selected feature set. And then this M is a feature indices. So we select one feature, then we just test of the HSIC of M's feature to its outcome Y. Is independent or not.
So XM would be one of the selected features that belongs in S? Or?
Okay, so S includes several features. So M is one of the indices in S.
Yeah, that makes sense. Thanks.
I will explain a bit more in details the later slides, but thank you for the questions. Okay, so this is the selective test frameworks. Then, so actually there's several approach, and then first I want to introduce about the simple approach. This is called the splitting method. So this is a simple solution. So basically the selective inference, the problem is that because we select some hypothesis from the data set, and then if we use the same data set to the inference, so this case we cannot control. So therefore, if we can somehow split the selection and the hypothesis testing, we can solve it. So this is the splitting method. So this is pretty simple. We simply split. So this is the original data matrix. This is N. N is the number of samples, and D is the dimension. And then we simply split data into 2, X1 and X2. For then we use X1 to select a set feature set or some like data set. Then we do the hypothesis testing rest of it. So in this case, we can split the selection and hypothesis testing. We can control the false positive rate. So, so this approach is fine. However, because we split the data, so this is because we are if we split the data, of course, we can use a small number of samples for selecting, also small number of samples for hypothesis testing. So therefore, the detection power can be degraded. So then the question is, can we do selection and inference without splitting data? So then the selective inference is really important. So in general, there are 3 types of selective inference approaches. So as I said, now there's one simple method. This is splitting method. This is simply split the data into 2. So this is extremely simple and also can apply to any approach, because we just need to split the data. Then we just do the feature selection or do something, and then we do the inference for another method. So therefore, this is very flexible. But only a problem is need to split the data. So another approach, this is based on the polyhedral lemma. This was proposed in Lee et al. Annals of Stats 2016. So this one can obtain closed form cumulative distribution, because for hypothesis testing, the p-value is important. So therefore, if we have a cumulative distribution, then we can do the hypothesis testing. So this is very nice. However, this one can only use simple model. So linear model and so kernel. So today I talk about kernel, but basically this polyhedral lemma can be only used for the simple model. Also, one restriction is that the response should be Gaussian. But so this is in general a problem for linear model case, but for kernel case, we can somehow handle this Gaussian response. So another approach is based on a knockoff filter. So this is proposed by Barber et al. Annals of Stats of 2015. So this one is another type of selective inference approach. So this one can use complex models. So like this, definitely we can use it for deep learning as well. However, this one, actually the knockoff filter is, we first generate some samples called the knockoff samples. Then we do some hypothesis testing. But actually the generating knockoff sample is difficult. So in this seminar, I mainly focus on the polyhedral lemma based approach, but actually you can use any types of method. So it depends on like what you want to use it. But basically all the methods, there's a pros and cons. But in this talk, I will focus on the polyhedral lemma approach. So here, until here, I just explained what is the selective inference and very general approach, how to do it. At this point, do you have any questions? If not, I just want to go. Okay, so then I want to talk about the selective independence test. And after that, the selective two-sample test and selective goodness of fit test. So basically, the approach is almost the same. Only the difference is what kinds of statistical measure we are using for testing. So independence test, definitely we use HSIC. Okay, so the selective inference independence test. So before I talk about selective independence test in details, I first introduce independence test. I think most of you know about what is an independence test, but just for the reminder. And so independence test, we have a set of data points like X and Y, they are paired. This is the input, this is the output. We have n samples. So null hypothesis is its joint distribution, Pxy, is equal to its marginal, product of marginal distributions. So this is the definition of independence. And alternative is just they are not the same. So this is a general independence test. So independence test case, people tends to use like HSIC or other types of independence measure to do the testing. So here, again, the selective independence test can be formulated like this. So we have, so this null hypothesis depends on the selected features. So basically, we somehow selected feature sets. So with this condition, then we do the testing whether two distributions are independent or not. So for example, we select some features, M's feature, then we check whether the M's feature is independent or not. So this is the selective independence test. So only the difference between the independence general classical independence test is that we select something, then we do the testing. So this is a difference. So more precisely, I use the HSIC. HSIC stands for the Hilbert-Schmidt Independence Criterion. So HSIC-based selective inference can be formatted like this. So we somehow select the feature sets. Then we check whether the HSIC is the X HSIC is 0 or not. So so actually we select the features. Then so M is a selected feature. Then we check whether the M features is independent or not. So this is the how to do the feature selection. Oh, sorry. So basically, HSIC is in 0 if and only if two X and Y are independent, right? So so therefore, we can use it as something like association measure to the features to this output. So therefore, if feature 1 is independent to Y, so this case, HSIC X1 to Y becoming 0. On the other hand, if X1 and Y are somehow dependent, then this can take some positive values. So this is the HSIC definition, right? So therefore, we can use HSIC as a feature selection measure. So so basically, the feature selection, we are using the feature ranking-based approach, or this is also called a sure independent screening or SIS method. We have data sets here. And so this is a d-dimensional vector. So each dimension, we compute the HSIC values. So we have 1, 2, up to D. So we compute D HSIC values. And then we select top M features by sorting. Sorry, this M is not the same as this M. Sorry, this is a typo. And so basically, this can be done by sorting the HSIC values and then just pick up some top R features. That's it. So this is the yes.
Sorry. So yeah, you select, let's say 10 features by selecting the ones with the highest HSIC, and then we say like let M equal to 1. And we're going to check if the first feature we've selected is, I mean, if the HSIC is going to be 0 or not, if it's independent or dependent, right?
Yeah.
But then if we check another M, like, do we need to do some correction because we're going to do multiple testings for the 10 different cases we considered? Or is the idea that we consider only one?
So thanks for that. This is a fantastic question. And yeah, of course, if we check all the 10 features together, we must do the multiple the correction. But if we do only one feature, we do not do the collection.
But then why would we want to select more than one feature in the selection event? Would the selection event be like we just pick one feature and then we test that feature? Or
yeah, that's okay. So yeah, I think generally, I think it's so if we think about all the features, 10 selected features important. I think we need to do the collections. But also, if we want to check whether only particular one features, then I don't think we need to do the collection. But Yeah, but I think in general, I think it's better to do the correction.
Mm-hmm.
Yeah. So I'm not sure whether I perfectly answered the questions, but basically we need to do some correction. But here in this talk, if I check only one feature, we do not do the correction in this.
Okay, so the setting we're considering is really we check if one feature is going to measure dependence or not.
Yeah, so if we check all the M's features all the features is in total, like check if we check all the features, I think we need to do the correction.
And I guess another thing that could be considered would be like we select 10 features, let's say, and then we concatenate them into a vector of 10 features, and then we test it for that vector. But like this XM could be like 10 dimensional with the features we've selected, like not depending on M anymore, where basically we've just removed all the features that were not interesting. Would that be a good idea, or do you think there's no point doing that?
So could you repeat the questions? So we simply concatenate the features.
Yeah, so I guess like what we're doing here is we start from like lots of features and we test only one feature.
Yeah.
But maybe we could have an HSIC with, so here X is just one feature, right? The XM. But maybe we could have some X here that depends on like multiple features, and that would be like all these features we've selected.
Oh, okay. I see. Yeah, that's also possible, but so in this talk, I will use the based on the polyhedral lemma approach. So in such case, we cannot handle the case. So if we want to select features and then we want to test all the features all together, this case, I think we can use the splitting method. But for the polyhedral lemma approach, I think it's a bit difficult to construct the hypothesis testing.
Okay, is that going to be because it's not going to be like the selection event is not going to be a polyhedron basically if we do
indeed
anymore? Okay, indeed. And then we cannot use. Okay, that makes sense. Thank you.
Yeah. Thank you for the great question. Okay, so So here I'll use the Hilbert-Schmidt Independence Criterion. So I think many of you know about HSIC, but just introduce the definition. So definition of HSIC is given by this. So this is a population version. And so, but this is we have a expectation. So therefore we need to approximate based on the samples. So there's several other HSIC estimations. And one popular approach is based on the V statistics. And so this is the proposed by Greton et al. And so this is computed in this way. So this K is a gram matrix for the input X, and L is a gram matrix for the Y, and H is called the centering matrix. And then we can simply compute by the matrix form. Also, another types of estimate is called the U statistics. So this is unbiased, Song et al., JMLR 2012. So this is given by this form, but this is unbiased. So basically, we use these test statistics for this. Basically, I use the U statistic base because this is unbiased. Okay, so here, from now, I want to explain polyhedral lemma-based approach. So, now I just set as the independence measure as I hat. So we employ an estimate of the independence measure. So this is any independence measure. And so now I just consider about the selective inference, selective independence test case. So Xi and Y. Okay, so and just write Z, this is a vector, the image vector. So this is the, each element of Z is some independence measure, estimate of independence measure. So 1, 2, 3D. So this could be like HSIC of first feature to output Y, second feature to output Y, and this feature and output Y. And we assume that this Z for a multivariate normal distribution, mu and sigma. So this is assumption. So now we have some independence measure. So this one follows the multivariate normal distribution. So this is the assumption at this point. So then I want to explain about polyhedral lemma. The theorem 1. So this is a consider stochastic data generating process Z. This is for the normal distribution of mu and sigma. This is given. So we just assume this one, and actually Z is this is a D-dimensional vector here. So if a feature selection event is characterized by this form, so I will explain what this means. But basically, if feature selection can be written by this form for a matrix A and vector B that do not depend on Z, then for any fixed vector eta, so this is any eta, we have these results. So this F is the cumulative distribution function of the univariate truncated normal distribution with mean T variance U. So this is the cumulative distribution and of the truncated normal distribution. So this one is the lower truncation points, and this is the upper truncation points. So this is the mean, this is the variance of it. And actually this one is the one we want to test. So this is the feature selection event. So this actually means that this is the cumulative distribution. So therefore, 1 minus this one is the p-value. So, and so this one follows the uniform distribution. Therefore, based on this cumulative distribution, we can do the hypothesis testing under this condition. So the good thing of this polyhedral lemma is that this lower and upper truncation point can be defined in closed form solution, closed form way. This one. Yeah. But the key point is the cumulative distribution can be given by a closed form. So I will talk about the intuition behind this polyhedral lemma in next few slides. So first, I want to describe why the selection event representation. So we use the sure independent screening case. So again, requirement is the output follows multivariate normal. So Z is the normal distribution, mu and sigma, and feature selection event can be written as AZ is less than or equal to B. So this is the one we use for the feature selection event. For example, feature ranking case or SIS case, we assume Z is, so this is a D-dimensional vector, and we denote the S, this is a selected set, and S bar is not selected set. So I is the indices of the selected set, and J is the indices of non-selected set. So in this case, the feature ranking selection event can be written in this way. So this Z I is the HSIC values of I's features. So this is the HSIC value of J's feature, because the ZI, so this one is the selected set, is already bigger than the non-selected set. So basically, HSIC is higher HSIC tends to be more not necessarily dependent, but it's a, so here we assume that bigger HSIC is more dependent to the features. So this is a selection event. So then, so we just reformulate this one, and GJ, GI is less than or equal to 0 for one set of J pair. And so this one can be written in this way. So we just prepare some vector here and multiply Z. So this is the one condition for the selection of I and J case. And actually, in I, we have several features. And for example, we have R features in S, and then in S bar, we have D minus R feature. So therefore, we have R times D minus R combinations of this one. So that can be the A. Then we can represent the feature ranking in this way. So here, A is a set of these vectors. Oh, sorry. And then B is just 0 vector. So this is a selection event for the feature ranking. It's clear? Okay. And also, so in this, also another case, of course, like feature ranking is so simple. Of course, we can use for the Lasso case. So Lasso stands for the least absolute shrinkage and selection operator. This is Lasso. So Lasso can be written by this way. And so this Y is a response, and X is input matrix, and W is the one we want to optimize it. So the Lasso is just simply the least square regression plus L1 regularization. So this lambda is some regularization parameter. So, and then by adding this L1 regularization, we can make W2 sparse. So then we can regard the non-zero element of W as the selected features. So here, we assume Y follow the multivariate normal distribution. So the previous particular lemma, I used Z, but here Y. So we just need to replace Z to Y, then we can use the for the Lasso case. And so for this case, the actual selection event can be derived from the KKT condition. So we compute the KKT condition for the selected feature set of W. Then we just plug this one into the polyhedral lemma. Then we can do the hypothesis testing for Lasso as well. Okay, so now we can characterize the selection, feature selection event in this way for the feature ranking and Lasso case. So actually this feature selection event is written as a polytope. So this one, because this is the just sets of linear equation, linear inequalities. So therefore we can form the polytope here. And so the key idea is so actually this one, eta transpose Z. So this is the one we want to test. So and so Z, so this one is the sets of HSIC values. And we currently assume this one for the multivariate normal distribution. So the key idea, because this is we assume this is the multivariate normal distribution. So therefore this is a linear projection to the 1D space. So then, because this is the normal distribution, also the 1D, this one is for the normal distribution. However, actually the feature selection event is a polytope. So therefore the solution must be in this polytope. And then, so let's say this line corresponds to this eta transpose Z, and we just map this Z to this place. So this doesn't look like a Gaussian, but just see this is a Gaussian. So actually this one distributed as Gaussian on this 1D space. However, because the values must be in this polytope, so therefore we need to cut this Gaussian distribution for the lower truncation point, upper truncation points. So therefore, so this is normal distribution. We cut at the lower and upper truncation. Then after that, we slightly compensate. Then, so this could be a truncated normal distribution. And then, so what is a p-value is that p-value is, because this is the one we want to test. So therefore, p-value is this region is a p-value. So therefore, we can compute the p-values. Then we can do the hypothesis testing. Okay, so then just this is just a check again. So because this is the most important part. So we have Z. This is the some Gaussian distribution from this is the HSIC values. And then we can represent the feature selection based on this sets of linear inequalities. And then in this case, we can compute the cumulative distribution, this one. Then we can do the testing. Okay, so I just want to mention that, so currently we assume that this mu and the sigma is given, and this is a true distribution, but basically we need to estimate this mu and the sigma from the data. For mostly, we set the mu to the 0, but the sigma case, we need to estimate from data. But this case, so we need to extend this for the asymptotic version. So actually, recently, our collaborator, Tobias, from the University of Cambridge now, he showed that the asymptotic case, a variant of polynomial lemma. So please check the in details for the ICML this year paper for the details. But basically, we can replace, we can use the estimate of sigma. Then still we can control, we can compute the p-values this way. Okay, so now I talk about how to this eta transpose Z part. Okay, so now we want to test case feature. Case feature is basically this one, right? So so this I is some independence measure, and so we are using HSIC values here. So actually the so this one can be written by this way, and because Z is a set of HSIC values for the features, so then we just simply set eta to the one hot vector. Only case feature is 1, 0 otherwise. Then we can represent this HSIC statistics by this way. Again, Z, so this one is a D-dimensional vector like this. So then now we can write the HSIC values. Then we can use the polynomial lemma to test. So also this representation is very nice because we can use other types of eta to do other types of the testing. For example, for this one, if you want to test only case feature, we just need to set the k to the one hot vector. But for example, you might want to, I don't know whether this is you want to test, but check whether case feature is better than the k prime feature. So in this case, we can simply set eta to 1 and -1. Then we can directly use the polynomial lemma and do the testing. So actually, this formulation includes many types of kernel-based tests. So this is one of a nice property of the polynomial lemma. So do you have any questions at this point?
I have another question. So at what point exactly do you choose the eta? Is it like after you've done the selection, you can choose any eta, or do you need to decide before, or does it make any changes in terms of level and correcting?
Yeah, I think you can decide any eta, but it must be independent from the selection or something.
Well, what do you mean independent of a selection?
So this is some fixed vector eta. So, but this one, if this is not depends on this one selection, then I think it's fine. If this is like maybe it's fine.
Because when you select one feature, like it needs to depend. Okay. It needs to depend on the features just to choose like which feature you select. Right?
Yeah, sorry, I was wrong. So basically, you can select any fixed vector here. This is fine. For example, the Lasso case, we okay. So Lasso case, basically what we do we first describe the selection event by KKT condition of Lasso. Then once we select the features, we just simply solve the least square regressions without any L1 regularization. Then we can form the eta based on the least square regression. But this can be different from the Lasso. And of course, we can use other types of eta. You can just set this one by your decision. But for the Lasso case, we first select this one by using the Lasso. Then we can do the least square for the testing. So this is also possible. So there's some, we can decide any, so my understanding, basically we can decide any eta here.
That makes sense, thanks.
Is that clear?
Yeah, thanks.
Okay, so can I go to the next one? Okay, so then, okay, so now, until now, I assume that the Z is for the multi-normal distribution, but actually it doesn't have to be, the estimate doesn't have to be follow the multivariate normal distribution. So, but actually we have a simple solution. Just go back. So basically until now, we simply assume this H values for the multivariate normal distribution, but it depends on what kinds of estimate of HSIC we are using it. For example, if we use the use statistic or V statistic is biased, so maybe it's not suited for the hypothesis testing, but for if you use a use statistics, so use statistics is fine. If the two distribution is different, then it's a normal distribution. However, if under the new, they are not normal. So therefore, we cannot directly use a use statistic. But the simple solution is to use the block HSIC estimator. So this one is proposed by John at the Statistics and Computing 2018. So this is a quite simple solution. So basically, we disjointly divide block data. So we have originally n number of samples. Then we simply divide into n over b block in disjointly. And b is some hyperparameters. B could be 10, or B could be 5, B could be 20. It depends on the, this is a user choice. And then the important thing is like we disjointly divide. And then we can have the n over b blocks. So each block have a b samples. Then block HSIC estimation can be written this way. So simply we compute use statistics of HSIC for each blocks and then simply sum them up. So this is the block HSIC estimator. So because we disjointly divide block, so therefore we can regard this as IID samples. So because this is sum of IID samples, therefore this is asymptotically normal by central limit theorem. So therefore this is, we can regard this as the normal distribution. So this is the simple solution. Then, so the basically we can use the block estimate. Then we can apply the polynomial lemma. Then we can do the testing. So another solution is that we can use the incomplete use statistics version. So this is also possible, but this one is much easier because we just need to split the data and then we compute the HSIC for each blocks. So the MMD version of incomplete use stats I explain later. So that's slightly easier, but for HSIC case it's a bit complicated because the use stats kernel is a bit complicated. But definitely we can use the incomplete version of HSIC as well. Okay, now we have all the components. So we first compute the HSIC based on the block estimate. Then we simply rank them. Then we can use the polynomial lemma. Okay, so I want to demonstrate some results of based on the synthetic data. First, we want to check whether we can control the false discovery. So here we set the input and output completely independent. So therefore, because this is independent, so therefore we want to make the we do not want to detect. We want, and then we set the significance level 5%. So therefore, we want to have the significance false positive rate at 5% here. So we compare three methods: split method and HSIC-Inf. This is based on the selective inference approach and HSIC. So as you can see, the post-selection inference approach, like split and HSIC-Inf, can control the false positive rate here. But this HSIC approach cannot control the false positive rate here. So again, this HSIC method is first select features based on the one data set and using the same data set to do the inference. So in this case, we cannot control the false positive rate. So therefore, we can discover more non-important features. So important part here is that, so because this is a non-parametric approach, if the number of samples is small, then in this case, it's a bit hard to control. But if we have a large number of samples, then we can control the false positive rate. Also, so this one, I use the block estimate. And so if we change the block 5 to 10, we can get almost similar results. But yeah, if we have large number of samples, then basically they are the same. So this is a true positive rate comparison. So I compare for the linear data, additive nonlinear, non-additive nonlinear. So linear data is just a simple linear regression case. So additive nonlinear is each component is nonlinear, but they are just the additive combination of nonlinear functions. Non-additive nonlinear can be like feature-feature interaction case. So here nonlinear is the feature and its output are nonlinear related. So this is a feature-feature interaction case. So then, so x-axis is the number of sample we used, and y-axis is the true positive rate. Higher is the better. Basically, equals to 1, this is the best. We compare three methods, HSIC-Inf. So this is the selective inference method. Split is also selective inference method. And LA-Inf, this is a selective inference method, but this is a linear method. For linear data case, so this case, the linear model performs the best. And on the other hand, our proposed method can get one good true positive rate if the number of sample is large. So this is very reasonable results because this is achieved the linear model. So therefore, this is performs the best. But our method can, if we have large number of samples, we can get a good performance. But for the additive nonlinear case, basically large inf doesn't perform well. This one can only detect the linear component, and nonlinear part they cannot. They all cannot detect this one. But on the other hand, split and HSIC-Inf can can detect the important features. Also, similarly, non-additive nonlinear, we can get the similar results. So for this experiment, as I said before, the HSIC-Inf can perform better than split method because we can use larger number of samples. So this is the true positive rate, and the bottom panels are the false positive rate. So again, if we have a large number of samples, then we can control the false positive rate for all the cases. So this is good. And we also run several real data analysis. I just show one. So this is a Turkish student evaluation data set. Because I choose this data set because this one has an output having 1 to 5 outputs. This means like response values. So 1 is maybe poor teacher, 5 is a good teacher. And because I picked this data, because this one, basically we cannot do a testing based on the typical linear method, linear selective inference method, because the political lemma, because we assume the Gaussianity for the outcome. But here, in our case, because we first transform the input feature and output based on the HSIC, and then we assume the Gaussianity for the HSIC. So therefore, we can still do the testing. So this is the result. So this black bold fonts are the kinds of selected features. So this is the p-values. For example, the 28 is the instructor treated all students in a right and objective manner. And this one having the p-values less than 0.001. So this is a significant, and this sounds reasonable. And so some of them are not selected as important. So here, so in the beginning, Anthony asked that whether we should do some correction, but here I didn't correct the p-values. Basically, I just examine each feature. So this is the without correction of the p-values. Okay, so this is a real analysis example. And I don't know how much I have. I think we already have 1 hour, but it's good to slightly speed up. Okay.
Yeah, I mean, in theory, we finish in about 5 minutes. But
okay, so
if you want to go on and
but
people want to stay, then I think that's also fine. So it's up to you.
Okay, so I think the most important part I finished. I just briefly wrap up maybe in 10 minutes. Is that okay? Okay, so then yeah, thank you. So then until now I explained about shear independent screening, but we can use other types of method. Like here I introduced the HSIC lasso. This is what I developed before. So this one is a bit more complicated than the screening-based method. So if we forget about this second or third term, so this corresponds basically the screening method, because we want to select alpha is some parameter, and then we want to maximize this HSIC values. And actually, if we solve this one to select some number of features, so this is just basically rank the HSIC values and select top 5 HSIC values. But this method, we have some penalizing part. So this is the some penalizing. Basically, if case feature and the K prime feature is similar, this value is high. So, and this is negative, but we want to maximize it. So therefore, like if the case feature and the K prime feature is similar, we just want to make alpha K and either alpha K or alpha K prime to 0. So then solving all the method, the object function together, then actually we can get feature sets that is similar to the response, but the selected feature sets are mutually independent. So this is the method called the HSIC lasso. Then, so actually this is a convex variant of MR method. This is a very popular data mining based feature selection method. Also, actually, the HSIC lasso can be regarded as sure independent screening. So basically, we can show that all the selected features is basically bigger than all the selected features of HSIC value is always bigger than lambda. Then we just simply selected mutually independent feature among the SIS selected method. So therefore, we can regard this one as one of the screening method. And then we recently developed the selective inference for HSIC lasso. So basically, this one is a lasso problem. Then we construct the selection event by KKT condition, then just using a political lemma. This is done by Tobias and Benjamin and Hector. And so this is the Okay. Okay. Thank you very much. I think then. So this is the results for the HSIC lasso-based results. Basically, this one can select less number of features. So this is a proposal method. We tends to have, very small number of features. And then this one is another approach based. This is also a proposal method. This is a political lemma approach. Basically, this approach, we can select small number of feature sets for the Turkish data set. Also, we apply this method for the some single cell RNA-seq data set. And then, so basically, we can select the we can select the same number of feature sets that the original study detected. The important thing is that one of the feature, this one is not selected in the original study. So therefore, maybe this feature can be useful.
Oh, wait,
okay.
Sorry, can I ask you a very quick question?
Sure.
What do you mean when you say that your proposal, you select fewer questions? Like, how does it work? I thought like you decide before how many features you want to select, and then you compute your things and you select the smallest, the biggest HSIC.
I see. Yeah, thanks. So this case, okay, so I need to double check the paper carefully. But basically, I think this case we fix the lambda. I think this depends on lambda values, and then I need to double check the paper. But basically, so this one we can detect. So okay, so this case we split into the data into three. One is for the because the original data is very high, so therefore we did the 3-step. First we do the feature selection based on the shear screening. Then we apply for the HSIC lasso based approach. And then so your question is why we can select small number of features, right? Here, right?
Yeah, because I thought how it works is just like you decide previously I want to select 10 features. So I understand that your method works better in the sense that, like, I don't know, if Q1 and Q2 are the same, it's not going to select it twice, basically. So like it's really cool. Just trying to understand the number thing.
Yeah, thanks. So I need to double check the paper, but basically it depends on lambda. I think we are by some the experiments we set relatively large lambda, I think, because of the setting. Then in the end we selected small number of features in the end, I think. So the other political lemma, this approach, this is a feature selection approach. So this case we can fix the number of selected feature in the beginning. So therefore we have
for your proposal, you don't fix the number. It depends on
no. Okay, so we just set some lambda. So therefore, due to that, maybe this is one reason that we tend to select small number of features. But
that makes sense.
Yeah, thank you for the questions. Okay, so it's almost like 1 hour. So but we have a bit more stuff. But basically, if you understand up to this, the rest of part is almost the same. So I want to explain about the selective two-sample test and the selective goodness fit test. So a selective two-sample test is basically we apply to the, we just make the two-sample test to the selective version. So this is the two-sample test, whether we check the P is equal to Q or P is not equal to Q. So this is a two-sample test. Then the selective version is just, we add the selection here. So two-sample test case, we can make the two cases. And basically the two-sample case, a two-sample test case, we can use the MMD. So, and then, so we check the, so, okay, so this case, we have two distributions, X and X prime. So we regard this is a class 1, this is a class 2. And then we check whether the features of M's feature of class 1 is different from the M's feature of class 2. So this is a test. And this selection is similar to what I did for the HSIC case. And then we apply the feature selection by using.
Just one more question.
Sure. Sorry, because I was too hard.
Should you also consider like x1 and x2 prime? So like because x1 is not necessarily matched to x1 prime, or like do you see what I mean? Because if P and Q are different, like there's maybe there's no like why would x1 like why would the first feature be mapped to the second feature?
Oh, okay.
I mean to the first feature of the second sample.
Okay. Thank you for but basically MMD case we regard the PX this is a d-dimensional vector, so this is also d-dimensional vector, and then each feature is like the same features, but basically different classes.
What do you mean each feature is the same feature?
Okay, so this is basically this is some class 1 data set, d-dimensional vector. So this is a class 2 d-dimensional vector. This is a binary classification problem. So this is the samples for all the class 1 data set. So this is a sample for all the class 2 data sets. And then, so they are the same d-dimensional vector, and each feature is the same for the, no, sorry, my English is not good. Each feature 1 is the same for the class 1, the class 2.
So it wouldn't make sense to compare x1 with x2 prime? Like I'm saying, instead of computing D MMD, should you compute D square MMD basically? Like doing all the possible matching. I'm not saying it's a good idea. I'm just trying to.
No. So here I just compare the first. So here, so this one is the first feature of the class 1. So this is the second feature, first feature of class 2. So I didn't compare the first feature to the first feature of MMD. First feature of this data set and second feature of this data set. But that's interesting questions. And maybe, yeah, that's also possible. But here I just consider about the binary classification problem. And yeah, we just test onto the, only first features. This is a common for both the cases. But yeah, that's very interesting questions. But that case, but the difficulty is like, because if we start considering the combinations, I think it's very hard to construct detect the features with the current approach, I think, because it's because we
especially have I guess if the dimension is quite large, when you have D squared to compute, and that can be quite a lot. Like so.
Yeah, but I think it's very interesting question. Thank you. Okay, so thanks. Then we did the feature selection. So this is done with the past intern, Danny. He's currently the PhD student at Toronto. Also, we can, I just explain about the feature selection case, but of course we can do the data set selection case as well. So instead of features, we can select which data is important or not. And okay, so I just want to skip, but basically we use the MMD, and we can use not use statistics. We can use incomplete version of use statistics, or just a block estimate of a use MMD estimator. And so this is the results. Basically, for this experiments, we found incomplete use stats is better than the block estimate. And we also did use this method for checking whether which GAN method is good. So this one, let's think this is the true images, and L is L's GAN's model, generated images, and we just check whether this is similar to the original image or not. And then, so I did this experiments in 2018. At the point, so there's several GANs, but it seems that none of the GAN was good, not that good. So therefore, actually, in the end, all the method was rejected. So therefore, none of the GAN was the same to the original images at the point. But actually, in this case, we cannot accept the null hypothesis. So therefore, we cannot say that even if we cannot reject, then we cannot say the same. But at this point, all the method was rejected. So therefore, it was, yeah, at least we can check whether the method is not good for this method by using MMD-based inference approach. Maybe currently the GANs is much better than at the time of 2018. So therefore, maybe we cannot reject in the end. Okay, so it's almost end. And then we also apply this to the goodness of a fit test. So this is just replacing the, okay, so this is almost same to the MMD case, but we have our data points from one distribution, and we have a model on the other hand. So we just select the models, and then we just test under this some model is selected. Okay, so this case we use the Kernel Stein Discrepancy. So this one we use the comparison-based testing. So this R is the distribution of the true data set. This PM is the one that was selected models. And so this testing means that we select best model, and then we check other model is good compared is good as the best model or not. So if we cannot reject this null hypothesis, so this means like maybe this PI model is as good as PI model, but of course we don't know yet. But if we reject it, this PI model is not good as the PI model. So therefore, like if the model is not rejected that much, then we can consider the model is good. So this
Sorry,
is
what's the PI? I got confused. Can you just repeat what the PI is?
Okay, so PM. So this is the best model. For example, best KSD model. No, smallest KSD model to the data set. So this and the PI is the rest of it.
Okay.
So best model and not the best model. So they are the same or not. So this is a test. So this is one because they employ this. We employ this model because so this case because this case all the model is not correct. So therefore this KSD is always for the normal distribution. So therefore still without using the block estimate, we can still do the testing. So therefore we do this types of testing for this particular case. Okay, so this is done with Jennings. He was a past intern. Also, I think many of you know the Vitawat. So this is mainly done by these two people. Okay, so this is the results of the density comparison experiments. So this is the truth data set. We have several other models. And then, so this is the results. So as I said, if the data is not rejected, tends to be the good model. So this is the results after the 100 runs. So from this one, as you can see, MOZ, MOZ2, this seems not a good model. So actually they are rejected a lot. So therefore this is not a good model. On the other hand, MOZ5, this one, and MAF, this seems like a fit to this model. So actually this is not rejected that much. So therefore we consider this is a good model. Okay, and this is a negative log likelihood of average over 100. And we just selected, this is the number one model after the experiments. Okay, so sorry, I passed the 15 minutes, but this is the conclusion. So in this seminar, I talk about selective inference for kernels. Basically, this is the selection plus the inference. And many testing frameworks can be written by selective inference. And so far we have proposed several selective testing frameworks: selective independence test, and selective two-sample test, and selective goodness of the fit test. So maybe I think this is the popular testing framework, but I think this political lemma approach can be used for the other types of tests if there are some good kernel-based estimator. And the future work is, okay, so as I said, so this talk, I mainly focus on the political lemma-based approach, but of course we can use a knockoff filter-based approach, also other types of approach as well. So this one just maybe we can just simply replace the political lemma part to the knockoff filter. So maybe this is not that hard. This is still like quite open problems for both the knockoff filter and the political lemma. Basically, the kernel method, because this is a non-parametric method, we need to have relatively large number of samples. So therefore, like if we have a very high dimensional case, we cannot detect lots of features based on our current proposal method because we need to have lots of samples. Also, currently, so this is like a question by Anthony. Basically, we do not consider about the feature-feature interaction at the point, because if we start consider about feature-feature interaction, this can be a very high dimensional. Therefore, we can detect the features. So therefore, still this is an open problem. And also, I'm a bit interested about the causal relation to the causal inference, because the HSIC is highly used in causal inference problems. So therefore, maybe it's possible to use some selective inference approach to the causal inference programs. Also, definitely we can consider about some applications, because p-values is used for everywhere for the science discovery literatures. So therefore, if we can develop very nice methods, maybe potentially, if we can find very important key finding based on this testing framework, then that's super cool. Also, this paper introduced several methods: HSIC-based method, MND method, and HSIC Lasso. And so this is a goodness of fit test. All the code available here. So I can share these slides later. So maybe you can check this paper, this software later. Also, finally, I want to acknowledge all the collaborators for this paper. I just put the main contributor to this projects, but without these helps, I couldn't achieve this goal. Thank you very much for listening to the seminar. Sorry, it takes 20 minutes over. So if you have any questions, please let me know.
Yeah, well, thank you very much. I thought that was great. Does anyone have any questions?